A7. This is more like much more of just like a thought process, right? And it's just simply thinking about what are the conditions that we're talking about, and then identifying what type of, you know, thermodynamic process is happening in these cases, right? And so it's more of a thought experiment in general, but it's to help you kind of identify keywords, right? Key concepts that are very, very important for understanding, and identifying like what's going on, and then because once you know that, right, and using what we had, already done for, B8 and stuff, we can, use that then as our way to kind of guide our process in these scenarios. So, going through it, right? So if we look at it, right, we have a piston, right? It has a gas inside of it, and then we have, a heat reservoir, on one side, and we have a cold reservoir on the other side. And so there's going to be different conditions that we're going to do, and that'll kind of tell us, what's going on. So, part A, it says, right, suppose that the hot reservoir has a temperature of 700 Kelvin and your gaseous system is also at 700 Kelvin. You allow the piston to move freely and for heat to pass through the hot reservoir in the system while remaining at the same temperature. What happens to the volume and pressure? So, first things first, right, looking at this right here, we should automatically be able to identify, right, we're in an isothermal process, right? We're staying at the exact same temperature. The surroundings are at the same temperature as the system we're looking at, right? So it's an isothermal process. So that means, right, and we're saying that heat is flowing into the system, right? And so if heat is flowing into the system, then that means that we should have, negative work in that case, right? And so if we have negative work, then that means that we're expanding, right? We're increasing the volume. And so then that means that the volume, right, should go up, right? The pressure has to go down in these cases. And right, temperature stays same. Right. And so, thinking about that right there, right, temperature stays the same, the volume goes up, the pressure goes down. We're not dramatically, right, changing the pressure, right? We're not changing it all on our own, or we're just completely, ripping it to a different pressure, right? We're just letting it happen gradually, right? And so that should give us an idea that what we're doing right here is a reversible process, right? Because we're not dramatically changing the pressure, right? We're letting the pressure change very, very slowly. In these cases, right? Same thing with the volume, right? That's changing very slowly as well. So that should tell us, right, that what we're looking at is an isothermal process and it's reversible, right? Because we're not dramatically changing the pressure, like all at once changing the pressure, right? We're very gradually, like infinitesimally small, changing the pressure in this case right here. So now, right, the next part of the question is, right, suppose to block the heat flow between the system and anywhere and let the system cool to 300K. What happens, right? So we're blocking any heat flow. So that means that now, right, Q, that should tell us, right, Q is going to be equal to 0 now, right, because there's no heat flow anymore. Q isn't changing. So Q is equal to 0. So if Q is equal to 0, right, that's telling us that this is an adiabatic process that we're looking at. And so it's an adiabatic process. We know then that the temperature is going to go down in this case, right? And we know that for, an adiabatic process, right, that you have T1, V1 gamma minus 1 is equal to T2 V2 gamma minus 1 in those scenarios. So if, the initial temperature is higher, right, we're at 700 Kelvin, and we let it just simply, cool down to 300 Kelvin in this case, right? So that means that those two are going down. Then that means that, for those things to stay equal, V2 has to go up. So we know then that the volume is going to go up. And if the volume goes up, that means the pressure has to go down. And we know that the temperature goes down as well, right? But we know it's an adiabatic process. And the other thing is, right, we know because, again, we're not dramatically doing this. We're letting it happen slowly, right? This is going to be a reversible process in this case. And so the next question, right, so now we let the heat flow happen right now with a cold system where we're at 300 Kelvin for the surroundings. And so now what's changed, right, is that there is now Q that is equal to is going to be non-zero now because it's attached to a reservoir. So it's not, completely isolated, right? It's just simply now in an environment that has the exact same temperature. So there is heat flow that happens. And so Q is non-zero. Right? But that's also going to tell us, right, that we're looking at an isothermal process. But in this case right here, right, we would then expect it, everything to be flipped. So, right. So, beforehand, what we were doing was an expansion. Now, right, what we would expect it to be is a reversible compression in this case, right? Because we're going to expect the volume to go down. We're going to expect the pressure to go up in this case. And so now, right, we let that happen. We let enough heat and work and stuff like that to happen. And so now we, reading through the problem again, we just simply, take it and let the system, do its thing. And so in that case, what we're doing now, right, is that we're going to be doing the exact opposite. Right now, what we're going to be doing is an adiabatic reversible compression, right? Because now again, right, Q is going to be equal to 0 because we're essentially, completely isolating the system. And so now, right, the pressure goes up, right, the temperature goes up, and so now the volume though continues to go down in that case, right? So we have this process right here. So now, right, if we're looking at this and we're thinking about it, right, we're starting back up again at the same temperature. We're going to be at the exact same volume and same pressure that we started off with, right? So the overall change, right, we just simply went in a simple cycle in this case. And so overall, right, delta E should be equal to 0, right? Because it's a state function. It doesn't matter what the path is that we get there, right? We just simply, drove around in a circle and we're ending up exactly where we end up, right? So the overall change in energy of the system should be equal to 0. There should be no change there. So if we were to draw this, right, what we have is that initially, right, we're starting off at this, a higher pressure and volume up here. We're initially going to be going through an isothermal, reversible expansion, right? So pressure goes down, volume goes up. So that's going to look something like this. The next thing, right, that we're going to be doing is go through an adiabatic reversible expansion, right? And so now that should have a different curve, right? That should be a little bit more dramatic in that case right there. Right, so we get this right here. The next thing, right, that we did is that we did then an isothermal reversible compression. So volume is going to decrease, pressure goes up, right? So that goes up like this. And so then finally, right, what we did is then an adiabatic reversible compression. And so then that should bring us back up to here again, right, where we're starting back off at the initial temperature, right, and volume and pressure. So, right, so that right there is what everything should look like in this case, right? And so, in this first scenario right here, right, we're having Q going into the system, and then in the second one, right, we're having Q go out of the system. In those cases, right? So we have that all right there. And so then now, right, in terms of the work that was done, right, all the work that was done was the area that's in here, right? And that's, what's referred to as the Carnot cycle. And so that's how you go there, right? So the big thing really is like looking at and identifying what are the keywords, what are the things that really tell us what's going on and everything in these scenarios. So yeah, but that's, how you approach, thinking about those problems and like what are keywords and what are things to kind of look for in those situations.